So tonight we're going to cover a few things on our way to the start of experiment 2, right? We're going to start off in this pre-lab lecture with an explanation of Avogadro's number, what it is, where it comes from, and why it is just so darn important, all right? It allows us to describe the atomic world, and it allows us to count in the atomic world. Then we'll take you through the mole concept, what it is, again, why it's so important. It is one of the most fundamental things that you will learn in chemistry that will translate into every other branch of your studies. Right? It'll be used in physics. It'll be used all over chemistry. I mean, we'll use it chapter 5, chapter 6, chapter 7, all the way through chapter 21 to describe all kinds of quantities. Then we'll take you through the molar mass. That's the mass you find up on the periodic table. We call it the molar mass because it has the units of grams per mole. So it describes the weight of 1 mole of the element. It's very useful. It allows us to describe the actual mass of a chemical formula just by the element's molar mass being additive. All right, and then we'll go through experiment 2, and we'll show you how you use and how you apply the mole concept to chemistry. All right, it'll give you an understanding of the enormity of Avogadro's number, but also why it has to be so large because we're describing something so small. In the atomic realm, Avogadro's number is a good depiction of a macroscopic world. So what we're going to start off with is Avogadro's number. Avogadro's number is equal to 6.023 times 10 to the 23rd. Now, our unit when we're talking about Avogadro's number depends on what we're talking about. So in our lab, you will use nickel sulfate right here, right? It's a blue substance. It contains a hexahydrate nickel sulfate, right? You'll use sodium chloride, just benign table salt, right? You'll also use ammonium sulfate, right? You'll use all kinds of chemicals, and you'll use these chemicals to see how this number changes. Well, it doesn't change, right? So we got a little bit of conflict there, but it'll be really cool for you guys. So when we use Avogadro's number, we always use it in tandem with the mole concept. So to talk about Avogadro's number is to talk about the mole concept. Talk about the mole concept, you have to talk about Avogadro's number. So when we're talking about this huge, ginormous number, you have to keep in mind how small it is, the thing that we are describing, right? So when we talk about times 10 to the 23rd, think about us talking about an electron, right? We said the mass of an electron was 9.109 times 10 to the negative 31, right? And that's an incredibly, incomprehensibly small number, right? We just can't comprehend how small that number is. So to describe a counting principle that counts that small of something, we have to use a very large number, right? That's why it's so large, and that's why we have to use it. So the mole concept is a concept that you've run into many times in your life, right? We've all used a baker's dozen. We've all used that. We've all used all kinds of different concepts with that, right? A classroom full. We've talked about a ton of, right? What do those words represent? Well, they represent a number of something, right? So a dozen represents 12. Baker's dozen represents 13. Well, that's exactly what Avogadro's number represents. That's exactly what the mole represents. So a mole, so we'll just say the mole. We're going to expand this definition, right, into bigger things. But the mole is equal to 6.023 times 10 to the 23rd of something. The mole is the unit used to describe this number. Because we don't always want to say 6.022 times 10 to the 23rd. We don't always want to say that, right? So using a mole to describe this number is a very useful thing, right? Because we'll use molar masses. We'll use mole fractions. We'll use all kinds of things that involve the mole and that unit describes this number. So let's do a couple examples, just some things that you run into in everyday life. So let's do a mole of stars, right? When you look up at the sky is covered at night with stars, right? So let's say 1 mole of stars, right? How many stars does that represent? Well, it's really easy. The mole kind of acts like a variable, like all units that we've been talking about. You can treat units as variable quantities or algebraic quantities. So when we talk about 1 mole of stars, right, we act like 6.023 represents that. A mole represents 6.023. So then we go 6.023 times 10 to the 23rd stars. This is equal to each other. So we say 1 mole of stars is equal to 6.023 times 10 to the 23rd stars. It's a really simple concept, and it should be easy to grasp. Although, I will say that it is one of the concepts that students struggle the most with. All right? This representation is very easy. It's a simple relationship. 1 mole of something equals 6.023 times 10 to the 23rd of something. Just like 1 dozen donuts equals 12 donuts. It will always equal that. It is a quantity, it is a unit used to describe a quantity. Just like we would use kilometer to describe 1,000 meters. You can go on and on with examples throughout our world, right? A mile to describe 5,280 steps. We have all types of quantities like this to make our life easier, pretty much, right? So as a chemist, we will use this number to describe a ton of different things. So it's easier to represent this number with a mole, as a mole, than it is to say that every single time, right? So we'll go through the molar mass, and it'll make more sense when we do that, right? But just keep in mind, as we move on, that 1 mole is equal to 6.023 times 10 to the 23rd. If you want an exact definition, go to your book, all right? Let's erase this. And we're going to keep that number up there as a reminder. This is always Avogadro's number. Will never change. It is accurate to 4 sig figs, though when we use it as a conversion factor, sig figs don't matter because conversion factors are considered to be exact numbers. All right, so 6.023 times 10 to the 23rd. Again, Avogadro's number. What does a mole equal? Equals Avogadro's number, right? We can have a mole of anything. I'll keep coming back to this. I'll keep hammering it home because, man, I tell you, this is a hard concept for people to get, all right? 1 mole equals 6.023 times 10 to the 23rd. A mole of desks equals 6.023 times 10 to the 23rd desks. A mole of humans equals 6.023 times 10 to the 23 humans. A mole of glasses means 6.023 times 10 to the 23rd glasses. A mole of posters means 6.023 times 10 to the 23rd. A mole of Twilight movies means death from above. All right? So the mole concept is intrinsically related to Avogadro's number. I think I've hammered that home enough. Let's move on to molar mass. Molar mass is I'll say this 1,000 times, but it is imperative to the science of chemistry. All right? It is the mass we use to take that microscopic atomic scale and turn it into the macroscopic scale that we all know and love, right? We don't want to work on the scale of protons and neutrons. We just don't. We can't. We're humans. We cannot work on that scale. So we have to take the atomic scale and move it to the macroscopic scale. And that's what the molar mass does for us. So we talked about isotopes and mass numbers and all kinds of different stuff. And what we talked about was the average atomic mass. And that average atomic mass comes into play for our molar mass. Right? So if I look up, let's take sodium for example, because we blew sodium up and that was cool. All right, we'll use sodium for our example. So sodium, right here, has a molar mass of 22.99. Well, you might say that's a very odd atomic mass, Mr. Bueller, especially considering you told us that the mass number was the combination of protons and neutrons. But look at your presentation, look at your lectures. 22.99 is the average atomic mass, which means it's the atomic mass averaged across all naturally occurring isotopes. So maybe we have an isotope of sodium that's 25, but then maybe we have an isotope of sodium that's 21. Well, it's the average of all the isotopes that get added together. So this is the average atomic mass. Well, all right, now you're asking me, well, what does that number represent? We'll always attach units to numbers that we use, right? This represents atomic mass units. Well, you might ask, what are atomic mass units? Well, I like the definition I gave you today. It's a completely arbitrary unit that we chose as chemists to represent, the atomic scale. We chose that an atomic mass unit would equal 1/12 the mass of a carbon-12 atom. And that's where we get atomic mass units. And like I said before, you might ask, well, that doesn't make any sense. Why is it so arbitrary? Well, it's not super arbitrary if you think about it. We're carbon-based life forms. Carbon, is everywhere around us. It's in the plastics. It's in the hydrocarbons. It's in the fuel that drive your car. It's in the coal that powers your home. It's everywhere. So it's actually pretty smart that we chose carbon to be our relative standard, right? So that's an atomic mass unit, AMU, right? So those are the units that we use up on the periodic table. When you see those red numbers down below and the average atomic mass, those are in atomic mass units. Well, then we go, okay, so how can we transfer this into the macroscopic world? Because still, even though we've given it a unit, we still can't deal with this on our real world issues, right? So if I use a little bit of salt, right? I have a tiny little bit of salt. If I take this out, how can I describe this in atomic mass units? Can I? No, because we're still in units that describe 1/12 the mass of a carbon-12 atom. I mean, it's such a small mass between the protons and neutrons that we couldn't describe that. We couldn't weigh this in atomic mass units. There's no way. So how do we bring the atomic scale into the macroscopic scale? How do we bring and make this atomic mass unit real? How do we do that? We do that with Avogadro's number and the mole concept. So again, those numbers off the periodic table are atomic mass units. So we use those atomic mass units, and now we take that atomic mass and we make a molar mass out of it. And you might say, what does that mean? Well, we're going to use Avogadro's number, which is a huge number, but remember, this is very, very small. We're going to use this number to describe a number of sodium atoms, right? So I'll tell you what I mean. We're going to use Avogadro's number of sodium atoms to describe 1 mole of sodium atoms. So we take a number and a unit that is so small we can't deal with it in human observation terms, right? We just can't observe that small of a number. And we use a number that can describe this in macroscopic terms because we have such a large amount of it, right? So we're going to say that 6.023 times 10 to the 23rd sodium atoms is equal to 1 mole of sodium atoms. And you might say, but that doesn't make any sense. That doesn't do anything for us. We still have atomic mass units. But here's where it gets good. Here's where the usefulness comes in. All right? 22.99 atomic mass units. Now we can say, okay, now we arbitrarily assign this. There's a ton of science that goes into this, but it's not important, right? Well, it is important. It lays the foundation for the mole concept, but it's not important for your use of it. You know, the layman, the average everyday person doesn't need to know that science, and it'll just cloud the subject. So if you want to know, come talk to me, I'll tell you. But otherwise, we're just going to move on with this assumption, right? We're going to assume that 1 mole of sodium atoms is equal to 22.99 grams. Mind blown, right? Well, if you understand how cool that is and how much of the world that opens up, it blows your mind, right? So 1 mole of sodium atoms is equal to 22.99 grams, right? So we get this and we say 1 mole of sodium atoms is equal to 22.99 grams. So what we have here is we have a relationship, correct? I mean, we do have a relationship. And what can we do with relationships? If you watched my videos on dimensional analysis, you know that this equality can now be transformed into a ratio. We can make conversion factors out of this. And that opens up everything, right? We can describe the amount of atoms in something with this unit right here. So let's put it into conversion factors. Well, then we get 22.99 grams of sodium over 1 mole of sodium. And you might ask where the E goes. MOL is the abbreviation of mole. So when we take this number, I'll separate this real quick for you so that you don't get confused and your eyes don't start wandering. So we've taken the atomic mass units. We've used Avogadro's number in the mole concept to describe a gram quantity or a number of atoms, right? So now 22.99 grams of sodium is equal to 1 mole. We can also do the opposite. We can say 1 mole of sodium is equal to 22.99 grams of sodium. Well, now what do you think that leads into? That leads into dimensional analysis, right? So now that we have a molar mass, we can make an equality, right? We take the atomic mass units, we use Avogadro's number in the mole concept to make a molar mass equality, then we use that equality to describe conversion factors, all right? And now that this video is getting on to about 15 minutes, past 15 minutes, I'm going to go from here with the next pre-lab lecture, all right? You can start on your pre-lab lecture. You can start to figure it out with that, and then the next video will be the rest.